Hello, welcome back to my YouTube channel. In this exam review video, I will be going over several practice problems ranging from substitution and elimination reactions, Fischer projection, isomer relationship problems, stability of alkenes, and how to assign E and Z nomenclature to alkenes. And finally, I will also go over chirality. So let's get started. So this section is about substitution and elimination reactions. And this question asks us to do a couple of things. First, we are asked to determine the operative mechanism or the prevailing mechanism in this reaction. We are equally asked to draw the product of the reaction and also use curved arrows to show how the reactants are converted into products. In other words, we are asked to draw the mechanism for these reactions. And lastly, if we want to draw product for elimination reactions, we are asked to determine both major and minor products. So whenever we want to determine the mechanism of this reaction, the first thing we want to ask ourselves is, what are the factors that could help us determine the mechanism of this reaction? One, we have the alkyl halide, so we should definitely determine what kind of alkyl halide we have. Then we should also ascertain what kind of nucleophile or base that we have. And these are the two major factors we should consider. Regarding the solvent doesn't really help us determine what kind of mechanism the reaction will go through. However, the solvent is good in that if you use a suitable solvent, then you will have an effective reaction with maximum yield. So what kind of alkyl halide do we have? First, we need to look at the alpha carbon, which is the carbon that the leaving group is attached to. Okay. Then, how many carbons are attached to that particular alpha carbon? In this case, we have 3. Therefore, this alkyl halide is a tertiary alkyl halide. And tertiary alkyl halides can do SN1 mechanism. They don't do SN2. They can do E1, and they can also do E2 mechanisms. The other thing we will consider will be the nucleophile or base. What kind of reagent is this? This is a strong nucleophile. Why? Because that oxygen has a positive charge. So that oxygen has a negative charge. So the negative charge on the oxygen is an indicative of excess electron density. So that means that's a very good nucleophile. Now, as a base, this is also a strong base. Now, to determine if your base is strong or weak, you need to look at the stability of the base. If the base is stable, then it means it's weak because it doesn't want to react, right? It's less reactive. But if the base is unstable, then it's considered a strong base because now it wants to react, it wants to get rid of the negative charge. And as such, it will be very, very reactive. So what kind of mechanism does a strong reagent do? So a reagent that behaves as a strong nucleophile and also function as a strong base can do both SN2 mechanism and E2 mechanism. So if you look at the corresponding mechanisms, the common factor here is E2. Therefore, our mechanism will be E2. So we can go ahead and draw the product of this reaction. So for E2 product, the base usually abstracts a proton from beta carbons. So this has the alkyl halide has different beta carbons. So we have, let's call this B1, and then let's call this B2. So these beta carbons are the same. These beta carbons here are the same thing. So beta carbons are the carbons that are directly attached to the alpha carbon. Okay. Whereas alpha carbon is the carbon that is directly attached to the leaving group. All right, so if we place the double bond, so we have to place the double bond between the alpha and beta carbon in order to form an elimination product. So if we place the double bond between those carbons, then we would have this alkene. Usually, you just have to draw the alkene, the double bond. The leaving group will not be part of the product. We can also choose to place the double bond here between this alpha and beta carbon. And if we place the double bond there, we would have another alkane product. So these will be the product of this reaction. Now, the question says that whenever we form elimination product, we should label the major and minor product. So major product is the more stable alkane, whereas the minor product is the less stable alkane. The more stable alkane, or the major product, is the alkane that has more substituents. So the more substituted alkane will be the major product. To determine the substituents on this alkane, you will look at how many carbons are directly attached to the alkane, with the double bond. So here it's 3. So we have this carbon, and this carbon. So this is a tri-substituted alkane. Tri-substituted. In the case of this other alkane, there are only 2 carbons that are attached to that double bond. Okay. These are the only 2 carbons that are attached to that double bond. So this is a di-substituted alkane. So the most substituted one is the tri-substituted alkane. Therefore, that would be the major product. And this would be the minor product. The most substituted alkane is also known as the Zaitsev product, whereas the less substituted alkane is known as the Hofmann product. So elimination reactions will always form the Zaitsev product as the major product. Now let's go ahead and draw the mechanism for this reaction. So my mechanism will show how both products are formed. So to form the major product, my base will pull off a proton from this beta carbon. This is our alpha carbon, and that's the beta carbon. So normally, we'll draw a curved arrow from the lone pair on the hydroxy group towards this proton to show that that base grabs that proton. Now, when it grabs that proton, the bond between the proton and the beta carbon will break, and the excess electron will form a double bond between the beta and alpha carbon, which will then go on to kick off the leaving group. Mind you, the beta proton and the leaving group must always be anti-periplanar to each other. Okay, in other words, they must point on opposite directions. They must be almost 180 degrees away from each other. So for example, if the chlorine is on a wedge bond, that hydrogen has to be on a dash bond, and vice versa. But you don't have to show stereochemistry in this case, since stereochemistry is not shown in our product. I'm just doing this to explain how the base abstract the proton and the positioning of the proton that is being abstracted by the base and the leaving group. All right, so when the base pulls that proton, then a double bond will be formed between the beta carbon and the alpha carbon. This beta and this alpha carbon. And when the base pulls that proton, the base will form the conjugate acid of the base, which is water in this case. And also we will have the chloride ion, which is the leaving group. The sodium cation will be attracted to the anion. And this would be the E2 mechanism for this reaction. So this mechanism shows how a Zaitsev product or major product is formed. So let's draw the mechanism to show how the minor product could be formed. So let's place this hydrogen on a dash bond, then that means this other hydrogen will be on a wedge bond. Again, we don't have to show stereochemistry. Okay, I'm not actually interested in this. We don't have to show the stereochemistry of these hydrogens. This methyl group should have a dash bond. If we must place the Cl on a wedge, then the methyl group should be on a dash bond. All right, so for the minor product to be formed, the base has to pull off a proton from this beta carbon. That carbon has 3 hydrogens. So the base will only abstract one of those hydrogens. So the hydrogen has to be anti-periplanar to the chlorine leaving group. So it has to point in the opposite direction as the leaving group. So when the base abstracts that proton, the bond between the hydrogen and the beta carbon is going to break, and the excess electron will form a double bond between the beta carbon and the alpha carbon, and the leaving group will be kicked out. And when this happens, we will form a less substituted alkene. Now, when the base pulls off the proton from the alkyl halide, it will form the conjugate acid of the base. And here we'll have the leaving group that is kicked out. And of course, the cation will be attracted to the anion. Now, if you're drawing mechanism of the reaction, you must show all of the product as well as the byproducts too. This is only possible when you draw mechanism. But if you're predicting just products in the box, you can only just put the main products and you can exclude those intermediate or byproducts. All right, let's go to the next question. The next question asks us to provide the product of this reaction as well as determine the mechanism of the reaction, and also to draw the mechanism of the reaction. So in this case, the first thing to do is to determine what kind of mechanism this reaction will go through. So to do that, we will need to first of all identify the kind of alkyl halide that we have, as well as the type of reagent we have. So in terms of alkyl halide, that carbon, this alpha carbon, the carbon that has the bromine, that carbon has 2 other carbons attached to it. So that means this alkyl halide is a secondary alkyl halide. And secondary alkyl halide can do all the mechanisms. You can do SN1, you can do SN2, it can also do E1 as well as E2. So let's consider the type of nucleophile or base that we have. Sodium acetate is a strong nucleophile. This is a strong nucleophile because that oxygen has a negative charge. That means that oxygen has excess electron density that it could use to attack the electrophile speedily and willingly and readily. And so, as a nucleophile, this is a strong nucleophile. As a base is strong if it is unstable, and a base is weak if it's stable. Although this acetate anion has a negative charge on the oxygen, that negative charge can be stabilized by resonance. So when a base can be stabilized by resonance or by size, it's considered a weak base. So that means this is a weak base. So we have strong nucleophile, but a weak base. So reagents that are strong nucleophile but act as a weak base can only do SN2 mechanism. And that's because substitution be favored over elimination. So in this case, the common denominator here is SN2. Therefore, this mechanism will go through SN2 reaction. This reaction will go through SN2 mechanism. So to draw the product of SN2 reaction or mechanism, you just need to replace or substitute the leaving group with the nucleophile. Okay. So to draw our product, we'll have this. And because it's SN2 reaction or mechanism, there is always inversion of configuration. So if the leaving group was originally on a dash bond here, the nucleophile will now be on a wedge bond. It will be on the opposite stereochemistry, which is in this case a wedge bond. So SN2 mechanism always experience inversion of configuration or stereochemistry. So let's go ahead and draw the mechanism for this reaction. So we'll draw the mechanism, we'll draw the curved arrow from the lone pair on the negatively charged oxygen, and that nucleophile will attack the alpha carbon from the opposite side as the leaving group. Then it will kick out the leaving group. So to draw our product, because it is the oxygen that attacks that alpha carbon, so I will draw the bond between that alpha carbon and oxygen. That oxygen is connected to this acetyl group. So I'll connect that oxygen to this group. And that will be the product of the SN2 reaction. So when the nucleophile attacks the alkyl halide, the leaving group is kicked out. So I'll go ahead and draw the leaving group. Since our leaving group is an anion, the cation will be attracted to the anion. So this will be a byproduct. Because we're drawing mechanism, we have to account for everything, account for all the charges as well as the byproduct. So let's go to the next question. So this question asks us to also predict the product of the reaction, as well as to determine the mechanism and draw the mechanism eventually. So to determine the mechanism, we need to consider what kind of alkyl halide we have. So the alpha carbon, that is the carbon that is connected to the leaving group, Cl in this case, has two other carbons directly attached to it. Therefore, our alkyl halide is a secondary alkyl halide. And secondary alkyl halide can do all the mechanisms. You can do SN1, SN2, E1, and E2. We then have to also consider what kind of nucleophile or base that we have. So because of the negative charge on the oxygen, we'll say this is supposed to be a strong nucleophile. However, bulky bases like potassium thiophene are considered poor nucleophile. In fact, we don't regard them as nucleophile. Why? Because when we talk about nucleophilicity, we're talking about speed, right? We're talking about how fast a nucleophile can attack the alpha carbon of the alkyl halide. And substitution reaction is generally sensitive to crowding, especially SN2 reaction is sensitive to crowding. So the bulky base or bulky compounds like this, because of their bulky nature, it's difficult for them to attack the carbonyl carbon fast because of steric hindrance. And as such, this reagent is generally considered a poor nucleophile, or we can say weak nucleophile. As a base, it's a very strong base. And the reason it's a strong base is because it is unstable. Negative charge on oxygen cannot be stabilized by size or by resonance. Therefore, this is very unstable. And as such, it's very reactive as a base, which makes it a very strong base. Now, reagents that are weak nucleophiles but strong bases, such reagent can only do E2 mechanism. And so the common denominator here is E2. Therefore, the operative mechanism of this reaction is going to be E2. So let's go ahead and draw the E2 product for this reaction. To draw the product, notice that there are two different types of beta carbons. Okay, so it's possible that we can place a double bond between this beta and alpha carbon, in which case a product will be this less substituted alkene. We can also place a double bond between this alpha and beta carbon, in which case product is going to be this Zaitsev product. Bulky bases like potassium thiophene prefers to abstract the protons that are attached to the less hindered beta carbon of the alkyl halide. And that's because of their bulky nature, this carbon is more exposed. And so it's easier for that base to pull off a proton that is attached to this beta carbon. In the case of this reaction, the Hofmann product will be the major product. So the Hofmann product will be the major product. Why? Because this can form faster. In the case of this other proton, the proton on this beta carbon, for that bulky base to abstract that proton, that bulky base will have to squeeze itself in between the two bulky groups, in between chlorine and methyl group. And so it's difficult to access this particular beta proton. And that's why the Zaitsev product is usually less favorable whenever we're doing an E2 reaction with the bulky base. So this is the more substituted carbon, Zaitsev product. So this is the more substituted alkene, which is the Zaitsev product. However, this is less favorable in this case. So we'll consider this as a minor product. This is the only exception. Whenever regular bases are involved in an E2 reaction, they always want to form the major product, the Zaitsev product as the major product. The only exception is bulky bases like potassium thiophene and LDA. Those will always form the Hofmann product as the major product. So let's go ahead and draw the mechanism for this reaction. So I'll show how the mechanism can form both of the products. So like I mentioned earlier, the proton, the beta proton that will be abstracted by the base has to be in the opposite direction as the leaving group. So if we place that proton on a wedge bond, then the Cl has to be on a dash bond. Okay. And if the Cl is on a dash bond, then it is the proton that is on a wedge bond that will be abstracted. So this proton has two hydrogens. This beta carbon has two hydrogens. But you don't have to show stereochemistry if the structure in the question doesn't have it. I'm just doing this for explanation's sake. So in terms of mechanism, because the Cl is on the dash bond, the base will abstract the proton that is on the opposite stereochemistry. That proton is the one that is anti-periplanar to the leaving group. When it does that, the bond between the proton and the beta carbon will break, and a double bond will be formed between the beta and alpha carbon, and then the leaving group will be kicked out. And so this explains how we form the Hofmann product, which is the major product. Now, when the base pulls off the proton, it will form conjugate acid of the base. So we're going to have tet-butanol as a byproduct, and then we'll have leaving group that is kicked out. Of course, the cation will be attracted to the anion. So whenever you draw a mechanism, always show all possible products, both the main product as well as the side product. So let's go on to show how the Zaitsev product is also formed. I don't have to show stereochemistry, but I'm doing this just for explanation's sake. So if this chlorine is on a wedge bond, then the hydrogen that will be abstracted from this beta carbon have to be on the opposite stereochemistry. So that hydrogen has to be on a dash bond. That means this methyl group will be on a wedge bond. Now, if you have the reverse, if this hydrogen were to be on a wedge and the methyl group is on a dash bond, then you will not have a reaction. Okay, because the base can only abstract a proton that is anti-periplanar to the leaving group. All right. To draw the mechanism, we'll have a base, potassium tetrodoxide. That base is going to grab this proton, which is anti-periplanar to the leaving group. The bond between the hydrogen and the beta carbon is going to break, and the excess electron will form a double bond between the beta and alpha carbons, and then this leaving group will be kicked out. When that happens, it will form a double bond between this alpha and beta carbon. Now, the alkene will lose its stereochemistry. Why? Because the sp2 hybridized carbons is trigonoplanar, and there are no stereochemistry whenever we're discussing trigonoplanar atoms. So when the base pulls off that proton, that base is going to form the conjugate acid of the base, and here we'll have the chloride leaving group. The cation will be attracted to the anion. So this will be the mechanism demonstrating how both alkenes are formed. Again, we say this is the major product because we're dealing with the bulky base. The major product is the Hofmann product. The Hofmann product is the less substituted carbon. This has just 2 carbons coming off of the double bond. Whereas in the case of this one, this is the Zaitsev product because it's more substituted. It's the more substituted alkene. It has 3 carbons attached to the double bond. So let's go to the next question. We're asked to determine the mechanism for this reaction as well as the product. So let's determine the mechanism first. The type of alkyl halide we have is such that the alpha carbon, that is the carbon that the Br leaving group is attached to, has 3 other carbons attached to it. Therefore, this is a tertiary alkyl halide. And tertiary alkyl halide can do both SN1 it cannot do SN2, but it can do E1 as well as E2. Now, what kind of nucleophile or base do we have? Alcohol is a weak nucleophile. As a base, it's also weak. It's a weak base because it is stable. Stable bases are usually weak bases. So reagents that are weak nucleophiles and also function as a weak base can do only SN1 and E1. And they do these mechanisms concurrently. So the common denominators here are SN1 and E1. Therefore, the operative mechanism of this reaction will be SN1 and E1. So we're going to have SN1 product as well as E1 product. So let's go ahead and draw the SN1 product. For the SN1 product, we will simply replace the leaving group with the nucleophile. Now for the E1 product, there should be 2. And there should be 2 E1 products. And that's because there are 2 different beta carbons. So we have this particular beta carbon. And then we have, so this beta carbon is on the ethyl group. And then the other beta carbon, this one is on the methyl group. So the methyl groups are the same. So we just have to choose one of those beta carbons. Now for elimination product, all we have to do is to eliminate the Br and place a double bond between this alpha and beta carbon. If we do that, then we would have this product. We'll have this alkene. And we can also place the double bond between this beta carbon and this alpha carbon. If we do that, we would have this. So this will be the E1 product. Now the question asks us to label major and minor product whenever we form elimination product. So every regular base, besides the bulky bases, every regular base would form the most substituted alkene as the major product. And the most substituted alkene is this one because it has 3 carbons that are attached directly to the double bond. So this is tri-substituted, and so it will be the major product because that's the Zaitsev product. This other alkene has only 2 carbons that are attached to the double bond. So it is the less substituted alkene. It is the Hofmann product. And so that will be considered our minor product. So in terms of mechanism, so we'll draw mechanism for both the SN1 product and E1. So let's start with the SN1 mechanism. In an SN1 mechanism, the first step is that the leaving group will leave, and it will form a carbocation intermediate. And this is our leaving group after it leaves. When the leaving group leaves and forms a carbocation intermediate, the next step is that the nucleophile will now attack the carbocation. So a new bond is formed between the oxygen and the carbocation intermediate. So I'm going to connect the oxygen directly to that carbocation. And that oxygen has a hydrogen as well as an ethyl group. Because of this, we will give that oxygen a positive charge, because oxygen has 3 bonds. Also, because oxygen is the one donating electrons, so we'll assign a positive charge to it. The bromide anion will be attracted to the oxonium ion. So we need to get rid of the positive charge. To do that, we will use our solvent. The solvent here is also ethanol. So this ethanol will be acting as a base, and the base will grab this proton. This bond will break, and the excess electron will go onto this oxygen, thereby neutralizing the positive charge on that oxygen. And when that happens, we'll form this ether as a product. Then when the base pulls off the proton, that alcohol will then form an oxonium ion. Because the oxonium ion is positively charged, the bromide ion will be attracted to it. Again, whenever you draw mechanism, you want to show all the intermediate, and also make sure that you account for all the charges. The charges on the left-hand side of each equilibrium arrow, or reaction arrow, should be balanced. So whatever you have on the left-hand side, the charges on the left-hand side of this arrow, for example, should be the same as what you have here. So here, this is 0. The net charge here should be 0. The net charge here should be 0. Also, your atoms should be balanced as well. So let's now look at the mechanism for the alkenes, for the E1 product. Let's start with the ZF, how we form the ZF product. So the first step of the mechanism of SN1 and E1 is pretty similar in that the leaving group will leave, and when it does, it forms a carbocation intermediate. The difference here is that instead of the ethanol acting as a nucleophile, it will now act as a base. So to form the Zaitsev product, which is the major product, that base must pull off a proton from this beta carbon. So there are 2 beta carbons. There is this one on the left-hand side, and there is this other one on the right-hand side of the positive charge. However, this beta carbon has 2 other carbons attached to it. So in other words, it's secondary. Whereas the other beta carbon, this other beta carbon has just 1 carbon attached to it. So the base will prefer to pull a proton from the higher degree carbon. That's the one that will form the more substituted alkene. So to form the more substituted alkene, the base will pull off a proton from this beta carbon. However, in this case, stereochemistry doesn't matter. Why? Because this carbon is flat, it's trigonoplanar. So it doesn't matter which direction the hydrogen is pointing out. Now, when the base pulls off that proton, the bond between the beta carbon and the proton will break. It will form a double bond between the beta carbon and the positively charged carbon, and we would have our Zaitsev product, which is the major product in this case. So we also have the conjugate acid of the base. Now, the bromide anion will be attracted to the oxonium ion. And this will be the mechanism for the major product. Let's draw a separate mechanism to show how the minor product will be formed, which is the Hofmann product. Let's start from this carbocation intermediate. So the base will pull off a proton from that beta carbon. So let's say the first step of the mechanism has already taken place. Then this base will pull off this beta proton. And then this bond will break and it will form a double bond between the beta and carbocation. And we'll have this Hofmann product. Then the conjugate acid of the base will be formed. And to make sure our charges are balanced, this anion will be attracted towards the oxonium ion. And this mechanism accounts for the formation of this particular alkane. So let's go to the next question. This one is about SN2 mechanism. So this question asks us to draw the mechanism for this SN2 reaction. And I will also ask to then explain why the nucleophile always does a backside attack in an SN2 mechanism. So to draw the mechanism of this reaction, I've redrawn the reactants here. So essentially what happens is that the nucleophile will attack this carbon, electrophilic carbon or alpha carbon, from the opposite side as the leaving group. And when it does that, this bond will break and the leaving group will be kicked out. So now that we have the iodine attached, we want to maintain the tetrahedral arrangement of that carbon, that sp3 hybridized carbon. So if the iodine attaches from this side, now the other substituent will be pushed towards the other side in order it will rearrange itself such that it will maintain the tetrahedral arrangement. And this will lead to what we call Walden inversion. So that's why SN2 reaction or SN2 mechanism always lead to inversion of configuration. So if the carbon is chiral, in this case, for example, this is S, the opposite chiral center is what we have in the product. So S becomes R and R becomes S in an SN2 mechanism where the alkyl halide, where the alpha carbon is chiral. You will always have inversion of configuration. Now, when the leaving group is kicked out, of course, we'll have it here, and the cation will always be attracted towards the anion. So let's now answer the second part of the question, which says, why does the nucleophile do a backside attack? Why does it attack from the opposite side? Now, the reason it does that is that in an SN2 mechanism, the nucleophile usually would do a backside attack because it's only then that the HOMO of the nucleophile can achieve maximum constructive overlap between itself and the sigma star orbital or the LUMO or the antibonding orbital of the carbon-bromine bond. So this is the reason why the nucleophile will always attack from the opposite side as the leaving group. So this is the sigma star orbital or the LUMO of the carbon-bromine bond. So those electrons, these lone pairs in this nucleophile has to be donated. And for that to happen, you must have an overlap. So the orbitals must overlap properly. And that can only happen when the nucleophile attacks from the opposite side of the leaving group. So let's go to the next question. This one asks us to draw the mechanism for the following reaction. Now, whenever we're drawing mechanism, you first of all need to determine what kind of mechanism your reaction will go through. We know that this is secondary alkyl halide, and methanol is a weak nucleophile that is also a weak base. Essentially, we know that the mechanism for this reaction is SN1 and E1. However, the question only presented us with SN1 product and no E1 product. And so a mechanism should account only for the product that we're given. So since we're only given the SN1 product, our mechanism should only account for those products. And because we're not given the E1 product, we should not draw the mechanism for E1 product. So let's go ahead and draw the mechanism. Now, since this is an SN1 mechanism, the first step is that the leaving group will leave. And when it does, it will form a carbocation intermediate. And then we'll have the leaving group here. However, carbocation intermediate has a trigonal planar geometry. In other words, the geometry of carbocation intermediate is such that it is flat. And because it is flat, the nucleophile can attack from either the top face or the bottom face. So our nucleophile is alcohol, specifically methanol. So that nucleophile can attack from the top face. If it attacks from the top face, we will place that nucleophile on a wedge bond. And if it attacks from the opposite side, from the bottom face, we will place the nucleophile on a dash bond. So because this nucleophile attacks or approaches the carbocation intermediate from the top face, we'll place it on a wedge bond. And since it's the oxygen that attacks that carbon, the oxygen is what we will draw next to that carbon. And that oxygen is connected to CH3 and hydrogen. And because of this reason, since the oxygen donates electron to the carbocation, we'll give that oxygen a positive charge. And since that oxygen is a positive, since we have oxonium ion, the anion will be attracted to the oxonium ion. Remember, you must always account for the charges at every step of the mechanism. Now, the next thing will be to get rid of the positive charge on that oxonium ion. To do that, we will then use the solvent. So the solvent also is methanol. So the methanol solvent will be acting as a base in this case. So this third step is deprotonation. It's an acid-base reaction in which the base will grab the proton, the bond here will break, and the excess electron will go to the oxygen, thereby neutralizing the positive charge on that oxygen. And eventually we would have a product. And when the base grabs that proton, it will form the conjugate acid. So we'll have this oxonium ion. Again, the anion will be attracted towards the oxonium ion. And this will be the mechanism for how this particular product is formed. So normally, if the stereochemistry here is the stereochemistry here is R, and this is R, and this is S. So this is telling us that in an SN1 mechanism, you will always have racemic mixture, a mixture of both or opposite chiral center. Racemic mixture. So let's go ahead and draw the mechanism for the other product. Again, the Cl will leave first. When that happens, you will form the carbocation intermediate. Carbocation has a geometry of trigonal planar. And trigonal planar means flat. Trigonal planar means flat. So once the carbocation intermediate is formed, the methanol nucleophile, which is the weak nucleophile, can also attack the carbocation intermediate from the opposite side. And it could do this attack because the carbocation intermediate is flat. When it does that, we will place that nucleophile on a dash bond. And we'll give that oxygen a positive charge. And with methanol, we can now use the solvent to deprotonate the oxonium ion, the intermediate product. Don't forget to draw your Cl minus here. So when this happens, we will have this other product. Then we will have these intermediates to our byproduct. Of course, this will eventually lead to the formation of HCl and methanol. You can show that if you want, but you don't have to. So let's go to the next question. This section is about Fischer projection. And here we're asked to assign R or S absolute configuration to these chiral centers. So let's call the first chiral center, let's call it P, and let's call this one Q. Now to solve this problem, we will need to first of all assign priority numbers. And to do that, I will need to redraw. It's always a good practice to draw out the atoms. Usually when you do that, you can see things very clearly. So starting with the chiral carbon P, we have hydrogen on this side, we have OH on this other side. Then we have carbon Q. This is Q here, this is P here. Then this has OH, and this has a hydrogen. Then we have carbon with 2 hydrogen atoms. That is joined to OH group. Now the chiral carbon P is connected to a carbon with a hydrogen and double bond to oxygen. So we must first of all resolve the double bond by converting it into a single bond. So to do that, break one of the bonds and attach single bonds on each of the atoms. So since oxygen is originally attached to this carbon, we'll place oxygen here. Since carbon is originally attached to this oxygen, we'll place this carbon here. So that's how to resolve this. Now, we will now consider the different groups, the 4 groups that are attached to each of the chiral carbons. So starting with this is one group that's attached to chiral carbon P. This is another group. This is another group. And the whole of this is another group. So there are 4 groups on that carbon P, which is what makes it a chiral center. So I will then go ahead and assign priority numbers. So let's call this group A. Yeah, let's call this A. And this one B. Let's make this C. And let's make this D. So starting with A, we're going to list all the atoms in each group that are connected to the chiral center. So starting with A, the first atom that is attached to the chiral center P is carbon. So I will write the carbon first. Now I will now consider the other atoms that are attached to that first atom in group A. The other atoms are hydrogen, oxygen, and another oxygen. Now I will list those atoms in group A in descending order of atomic number. So starting with O, another oxygen, then hydrogen. Now let's go to B. B has OH, that's the OH group. Of the atoms in that group, oxygen is what is directly attached to the chiral carbon P. I'll write the oxygen, and then we'll have the hydrogen. Now let's go to C. C has so many groups, but the atom that is directly attached to the chiral carbon P is C. So I will list that first. Now I'm going to list the other atoms that are directly attached to that carbon C. So we have hydrogen, carbon, and oxygen. And I'm going to list those atoms in descending order of atomic number. So oxygen have the highest atomic number, so I will write that first, followed by carbon, then followed by hydrogen. Then lastly, D. D has just hydrogen. After listing the different atoms in each of the groups, I will now compare each atoms in the respective columns, starting with this first column. Priority number 4 will go to hydrogen. Priority number 1 will go to oxygen. So B gets priority number 1, D gets priority number 4. Priority number 2 could go to C or this. So since we have the same atom, there's a tie. Wherever there's a tie, you have to go to the next atom. So the subsequent atom here is oxygen. Here also is oxygen. We have to keep going until there is a difference. Now, since there is also a tie here, we'll have to go to the next atom. So the next atom for C is carbon, for A is oxygen. So priority number 2 is going to go to oxygen, which is A. So we give A priority number 2. And priority number 3 will go to C. Having done this, I'll then go ahead and redraw all of this based on the priority numbers. Now, this is looking very rough, so I have to redraw it to make it look a little bit neat. So you can do that based on the atomic number, based on the priority numbers rather. So A is here, we have B here, we have C here, and then we have D. So I will redraw this based on the priority numbers. So we say that A is priority number 2, B gets priority number 1, C gets priority number 3, D gets priority number 4. If we convert, let's convert this to actual Fischer projection. In Fischer projection, the horizontal bonds are generally regarded as wedge bond, and vertical bonds are considered dash bond. So I'll redraw this based on the wedge and dash. The horizontal bonds are wedge bond, and vertical bonds are dash bonds. So this is the actual Fischer projection. However, in order to assign the R or S absolute configuration, we need to convert this Fischer projection into a more relatable three-dimensional projection. So the three-dimensional projection that we're used to, normally we have 2 wedges and 2 lines. So I can choose any of these wedges to remain as a wedge, in which case the other bond will be on the line bond. So let's make 1 to be the line bond and 4 to be the wedge. Between 2 and 3, I will choose one of them to remain as a dash bond, and the other bond automatically will become a line. So let's make 3 to be the dash bond. Now that means 2 is going to be a line bond. So we can now convert this to a proper tetrahedral structure. This is looking like 90 degrees right now, but in a tetrahedral arrangement, we know that the angular distance is 109.5. So I'm going to redraw that as I will redraw that structure based on the ideal angular distance. So the ideal tetrahedral arrangement will have this kind of bond or this kind of angular distance. Now, wedge and dash bonds usually point along similar direction. Now, I can go ahead and draw my arrows, but because group 4 is on a wedge bond, I can just ignore group 4 draw an arrow connecting groups 1, 2, and 3, and whatever configuration that gives me, I will invert it. So in this case, this is a clockwise direction. Because it's clockwise, it should be R. However, because group 4 is on a wedge bond, I will invert this configuration, and that becomes S. Therefore, the answer to this problem, in this box, we should have S. So let's go ahead and do the same thing for this one. The next thing will be to assign an absolute configuration R or S to this particular box. That is to the chiral carbon Q. So I'm going to have to redraw that. We should have a hydrogen here. OH. This is OH, this is hydrogen, and this is CH2OH. So let's go ahead and redraw this. Just draw out all of the atoms. So this is P and this is Q. So starting with the carbon, chiral carbon P. So this is hydrogen here. This is OH. Carbon, hydrogen. Oh no, this should be OH. Hydrogen, carbon, hydrogen, hydrogen, then OH. On carbon P, we have a carbon that has one hydrogen and a double bond to oxygen. So we have to resolve that double bond by breaking one of these double bond, break the pi bond, and connect two bonds on each of these atoms. So oxygen will be here and carbon will be here. So now we're interested in Q. We're interested in this particular chiral carbon. So this is the carbon we're interested in. Now there are 4 different groups on that carbon. We have this hydrogen, and we have this. So let's label this as A. Let's make this B, C, and D. So I'll go ahead and list the atoms in each of those groups, starting with the first atom. So for group A, the atom in group A, the first atom in group A that is directly connected to the chiral carbon Q is carbon, is C. Now, if you consider that chiral carbon, if you consider that C, the first atom in group A that is attached to the chiral carbon Q, that has 3 other atoms that are directly attached to it. We have oxygen, this hydrogen, and this carbon. So we have to list those 3 atoms in descending order of atomic numbers. So starting with oxygen, carbon, and hydrogen. Let's go to B, group B. In group B, we only have 1 atom, which is hydrogen. Then we go to group C. In group C, we have carbon. Carbon is the atom that is directly attached to the chiral carbon Q. So I'm going to list carbon. Now, that carbon has 3 other atoms that are directly attached to it. So I'll list them in descending order of the atomic number, starting with oxygen, followed by the 2 hydrogens. Then group D. Group D is the hydroxy group. And in that group, oxygen is what directly attaches to the chiral carbon Q. So I'll list oxygen, then followed by the subsequent atom that is attached to it. Now that I've finished listing all the atoms in each of the groups, I will then go ahead and compare the atoms in each column. Group 4, priority number 4 rather, will go to the hydrogen because hydrogen has the lowest atomic number. So priority number 4 goes to B. Priority number 1 will go to this oxygen because it has the highest atomic number. So we give that oxygen, we are going to give group D priority number 1. Priority number 2 can go to either this carbon or this one, but because there is a tie, we go to the next atom. Since there is also a tie, we go to the next atom. So carbon has a higher atomic number than hydrogen, so priority number 2 will go to group A. Therefore, priority number 3 will go to group C. So I will now go ahead and redraw my compound, the structure, based on the priority numbers. So in terms of Fischer projection, this will be A, this is B, this is C, and D is here. So let's replace the alphabet with the priority numbers. So A has priority number 2, B has priority number 4, C has priority number 3, and D has priority number 1. In Fischer projection, let's redraw this as a proper Fischer projection. In Fischer projection, the horizontal bonds are wedge bonds. So I'll redraw those as wedge bonds. And the vertical bonds are dash bonds. So I'll redraw those ones as dash bonds. So in order to effectively assign the absolute configuration, we need to convert this Fischer projection to a proper three-dimensional structure. And a three-dimensional structure in a tetrahedral arrangement, you will have 2 line bonds, and the other bonds will have wedge and dash bonds. So let's make this one, let's leave it as the wedge bond, the one with the priority number 4. So that means the group 1 will be on a line bond. This time around, let's make 2. Let's leave 2 as the dash bond. That means 3 will be the line bond. So we should redraw this. Let's convert it to a proper tetrahedral geometry. That means this bond should be 109 instead of 90. So I'll redraw that. So if this is my group 3, group 1 should be this way. Now the wedge and dash bonds should face similar direction. So this is group 4, then group 1, and group 2 rather, will be on the dash bond. So this is what we will have. Now, because group 4 is on a wedge bond, I can ignore group 4, draw an arrow connecting groups 1, 2, and 3, and whatever direction that gives me, I will invert the configuration. You should only invert configuration whenever group 4 is on a wedge bond. So the direction of this arrow is counterclockwise. Counterclockwise means S. If you invert it, you should have our absolute configuration. I will then go ahead and place our configuration in this box. And this will be the solution to this problem. So let's go to the next question. This section is about isomers. and we're asked to compare relationship between two compounds. In order to compare effectively, we need to make sure that all of the substituents are in similar alignment. For example, in this case, in this structure, bromine is on the left-hand side. Here, bromine is on the right-hand side. The NH2 group here is on the right-hand side. The NH2 group here is on the left-hand side. So you want to orient the compounds so that the substituents will align properly. So to do that, I will keep this stationary and I will work on this. So the question would then be, how can I orient this molecule in such a way that the substituent would align just like the one on the left-hand side? So what I would do would be to flip this molecule along the vertical axis. I should flip it along the vertical axis. And whenever you flip a compound, the stereochemistry will change. It's just like let's say you have this individual. Okay, so if you flip this individual along the vertical axis, here, this is facing us. When you flip him, he will now be backing us. But the only difference is that the left hand here will now be, so the right hand here, this is his right hand. His right hand, that is on my left. When you flip him, his right hand will now be on my own right. But the key thing is that whenever you flip along the vertical axis, whatever is facing you now backs you, and whatever is backing you now will face you. So based on this compound, let's number this actually. So if you number this as 1, 2, 3, 4, 1, 2, 3, 4. Because we start numbering from the end that is closer to the bromo group, we should do the same thing for the other one. We should also start numbering from this end that is closer to the bromo group. So when we do that, we would have, so number 1, carbon 1 will now be here. This will be 2, this will be 3, this will be 4. So the NH2 is on group 3. So we're going to place the NH2 on group 3. But because the NH here is on a wedge bond, when we draw it here, when we flip it, it will now be on a dash bond. The bromo group is on group 2. Because the bromo group here is on a dash bond, it will now become a wedge here. So we can now effectively compare the compound. Bromine is on the right, NH2 is on the right here, NH2 is on the right hand here, and bromine is on the left hand here, and the bromo group here is on the left hand. So we can compare this easily. Now comparing them, this is different. So we have opposite stereochemistry or opposite configuration. And here we have also opposite configuration. So because the configurations or stereochemistries are different for each of the groups, the relationship between this compound will be enantiomers. They are mirror images. So those two compounds will be regarded as enantiomers. So let's go to the next question. So the next question asks us to ascertain the relationship between these two compounds. Here, NH2 is facing down. Here, the NH2 is facing up. The bromo group here is down, bromo group here is up. So we want to orient one of these compounds in such a way that both substituents will point in the same direction. So to do that, let's keep this one and then let's rotate this other compound. So the question then becomes, how can I rotate, or how can I reorient this compound in such a way that the substituent will properly align with the one on the left? So what I might need to do would be, I might need to flip this molecule along the horizontal axis. So if I flip it along the horizontal axis, it will change. The stereochemistry will change rather. So let's number this as 1, 2, 3, 4. It's always a good practice to number your carbons. It allows you to see things clearly. So if I flip it that way, then so we're going to have this. Now the NH2 that is on a wedge bond on carbon 2 will now become a dash bond. And the bromo group that is on the dash bond will now become a wedge. It will now be on a wedge bond. So if you compare these two compounds, you will notice that they are exactly the same compound. So the relationship between this compound is such that they are the same thing. But the key thing here is to know when and how to rotate or flip your molecule. Know when to flip and when to rotate, and which direction to do the flipping and rotations. So let's go to the next question. So this question is asking us for the relationship between these two compounds. Now I can see that the connectivity of this compound is different, right? And that's because here I have NH2 on carbon 2. Here I have put NH2 and bromo group on carbon 2. Okay. And in this case, bromo group is on carbon 3. Here, bromo group is on carbon 2. So the connectivity is different. But do they have the same number of atoms? Do they have the same molecular formula? Let's see. The total carbon on this structure is of 1, 2, 3, 4. So this has 4 carbons. How many hydrogens does it have? We have 3 hydrogens here. We have 2 hydrogens here. We have no hydrogen here. We have 3 hydrogens here. And we have 2 hydrogens here. So total hydrogen is 2 plus 3, which is 5, plus 2, 7, plus 3, 10. So we have 10 hydrogens. We have 1 nitrogen and 1 bromine. So let's see the other compound to the right. This also has 4 carbons. It has, in terms of hydrogen, we have 3. We have, this one has 1 hydrogen. We have 3 hydrogens here. And here we have 2 hydrogens. The total number of hydrogen is 3 plus 1, which is 4. 4 plus 3, which is 7. 7 plus 2 is 9. Okay, so number of nitrogen here is 1, and then we have 1 Br. So notice that the molecular formula of both structure is different. And if it's different, then these are not isomers. They are not isomers. To be isomers, the number of atoms in both compounds must be the same, and they must have the same molecular formula. All right, let's go to the next question. In this question, we're asked to identify the relationship between these two compounds. It's always a good practice to number your carbons, the carbons on the main chain. So here, the NH2 here is facing down. Here, the amine is pointing up. And the bromo groups are pointing in opposite directions. So we want to orient one of the molecules such that both of them will have their respective substituent properly aligning. So to do that, the question would then be, how can I flip? So let's keep this one on the left stationary, and then let's perform some operation on this one on the right. So the question then becomes, how can we, what do we need to do to this molecule to make sure that the substituents are properly aligning with themselves? So I will need to also flip this compound horizontally. If I do that, I'll have 1, 2, 3, 4. The NH2 will now be on a dash bond. Whenever you do a flip, the stereochemistry will change. And the bromo group will now be on a wedge bond. So if you now compare these, the NH2 here is different. The bromo group here is the same. So when you have some configuration that are different configuration or stereochemistry, and you have some stereochemistry or configuration that are the same, the relationship between such compounds will be diastereomer. So these compounds are diastereomers. Let's go to the next question. To determine the relationship between these two compounds, let's start by numbering the main chain. Always number the same way. The way you number the compound on the left, you should do the same for the compound on the right. So because I start numbering from the end that is closer to the substituent, I have to do the same in this other compound. So the next thing would then be the operation to perform on this compound to make the substituents to align with the one here is that we need to rotate this molecule. And whenever you rotate a molecule like this, the stereochemistry will remain the same. So let's rotate it such that group 1 will be here and group 4 will be here. So we're rotating it that way. If we do that, so group 4 will now be here. Group 1 will now be here. So the substituents are on carbon 2. So let's finish numbering this. So whenever you rotate like this, stereochemistry will remain the same. And the idea is that, so let's say we have this young man is laying down. If you rotate him, okay, if you rotate him by, let's say, 360 degrees, or 180 rather, then He's pointing in this same direction. The thing to note here is that the face, both here and here, is facing upward, right? So in terms of stereochemistry, whenever you make a rotation around axis like this, the stereochemistry remain the same. So that means we will have our NH2, because NH2 is on a dash bond here, it will remain dash here. Bromo group is on a wedge bond. You leave it as a wedge bond. And if you compare these two compounds, they are exactly the same thing. Let's go to the next question. This section is about alkene E and Z nomenclature, as well as stability. So the question here asks us to assign E or Z to these different alkenes. And to do that, let's start with A. The first thing is that draw a line dividing the alkene double bond into two equal halves. On the carbon to the left, on carbon 1, we have two groups, fluorine and CF3 group. Fluorine has a higher atomic number than carbon, so we're going to give this priority number 1. So that fluorine has the higher priority. On the groups on the right hand side, bromine has a higher atomic number than carbon, so we're going to give this group the higher priority. Now, when two groups are facing the same side, we'll assign Z. Okay, Z is derived from the German word, which means, which is zusammen. Zusammen is the German word that means together. Okay, so when two groups are on the same side, there's I have a quick memory trick here. When they're on the same side, I'll just assign Z or Z. Then E is derived from the German word Entgegen. I'm not sure if I'm saying that correctly. And this literally means opposite. And so the quick memory trick here to help remember this is E. You can assume that E stands for enemies. And enemies are on opposites. They're usually on opposite sides. So whenever the priority groups are opposite, we will assign E. And whenever they're on the same side, we'll assign Z. So in the case of A, because the priority groups are on the same side, we'll assign Z. Let's go to the next one. For the compound in B, again, draw a line dividing the carbons 1 and 2 into left and right. On the left-hand side, we have the CF3 groups, the CF3 group and the ethyl group. So both groups have carbon as the first atom that are directly attached to the carbon 1. So because there's a tie, we'll go to the next atoms. The next atoms here is fluorine. The next atom here is carbon. And fluorine has a higher atomic number than carbon. So this group will assign the priority, we'll make that group the priority group. On the compounds to the on the substituents or groups to the right, on this group we have carbon directly attached to carbon 2, and here we have fluorine. So fluorine has a higher atomic number than carbon, so the priority group will be this. Because in this case, the priority groups are opposite, we'll assign E. We will assign E. For this one, draw a line dividing the alkene into 2. Here we'll have up and down. So carbon 1 and carbon 2 will be up and down. On the groups above, we have CH3 and we have NH2. Now, if you look at the first atom that is attached to C1, nitrogen has a higher atomic number than carbon. Therefore, this group will get priority number 1. On the groups at the bottom, we have bromine here, and then we have sulfur and H in this group. Between bromine and sulfur, bromine has a higher atomic number than sulfur. Therefore, the bromo group will be assigned the priority group. In this case, the priority groups are opposite each other. Therefore, we'll assign E to this alkane. For this last one, again, draw a line dividing the alkene carbons into up and down. For group 1, carbon 1 rather, there are 2 groups, the OH group and the Cl group. In the OH group, the atom that is directly attached to carbon 1 is the oxygen. And here we have only Cl. Cl has a higher atomic number than oxygen rather. So we're going to assign priority number. We're going to make the Cl group the priority group. Of these 2 groups that are on carbon 2, fluorine has a higher atomic number, and so we'll make this the priority group. Because these groups are opposite, the priority groups here are opposite, this will also be E. So let's go to the next questions. This question asks us to rank these alkenes from most stable to the least stable. Now, most stable alkenes are usually the most substituted alkenes. So the more an alkene is substituted, the more stable it will be. So we can determine the substituents on this alkene by looking at how many carbon are attached to the double bond. So in this compound, in this alkene, we have 1, 2, 3. There are 3 carbons attached here. So this is tri-substituted alkene. In this alkene, there are 2 carbons. So this is a di-substituted alkene. In this alkene, there is just 1 carbon that is attached to the double bond. So this is a mono-substituted alkene. And in this alkene, there are 1, 2, 3, and 4 carbons. So this is a tetra-substituted alkene. So the most substituted alkene here is D. So this will be the most stable. The least stable will be the one that has the least number of substituents. And that's going to be this. So in terms of ranking, from most stable to least stable, it will be D, followed by A, followed by B, followed by C. So we're ranking these from most stable to the least stable. Let's go to the next question. This one is about chirality. So we're asked to determine whether these compounds are chiral or not. So an easy test to determine chirality here is, there are 2 actually. One, does the carbon have 4 different groups? If it does, then it's chiral. If it doesn't, then it is non-chiral or achiral. Another thing is plane of symmetry. Does the molecule have a plane of symmetry? If it does, it is not chiral or achiral. But if it doesn't have a plane of symmetry, then it is chiral. Starting with compound 1. This carbon here has 4 different groups. There's a hydrogen, an implicit hydrogen that is not shown. So we have one group, group 2, group 3, group 4. So there are 4 different groups on that carbon. Therefore, we will say that this compound is chiral. Another way to tell is that there is no plane of symmetry. You can't divide this compound into 2 equal halves. So next question. Looking at this compound, the groups here and group here are the same. So definitely there are no 4 different groups in that compound. Therefore, this compound cannot be chiral. Secondly, in terms of plane of symmetry, you can literally divide this compound into 2 equal halves. Therefore, this will be achiral. For this compound, we can, although this carbon and this carbon are chiral carbons because they have 4 different groups attached, there is a hydrogen here that will be on a wedge bond. Okay, so that means this is 1, 2, 3, and 4. So there are 4 different groups on that carbon. That particular carbon, that specific carbon is chiral. If you look at the other carbon as well, so if you look at this other carbon, there is also an implicit hydrogen that is not shown. Notice that there are also 4 different groups. So that carbon is also chiral. But this molecule actually have a plane of symmetry. And that's because you can easily draw a line to divide this compound into 2 equal halves. This half and this half are exactly the same thing. So this is a meso compound because it has a plane of symmetry. Therefore, this is meso. Meso compounds are generally achiral. So let's go to the next question. Again, these carbon are chiral centers specifically. However, you cannot divide this compound into 2 equal halves. If you draw an imaginary line dividing this compound, this half and this half are not the same. Why? Because this OH group is on the dash bond. This one is pointing in the opposite direction. So this is chiral. Next question. To answer this question, it will make a lot more sense to redraw this as just cyclohexane. So convert it from the chair conformation to this hexagon. So if you number these carbons as 1, 2, 3. So we're going to assume that whatever is pointing up will get a wedge bond, and whatever group is pointing down will get a dash bond. So on carbon 1, the methyl group is pointing up, so we place it on a wedge bond. On carbon 2, the methyl group is pointing up, we place it on a wedge bond. On carbon 3, the methyl group is pointing down, so we're going to place that on a dash bond. So for this compound, we cannot divide this compound into 2 equal halves Because if you draw this side and this side are different. So we have two different halves. Therefore, there is no plane of symmetry. No plane of symmetry. That means our compound is chiral. Again, if you check each of those carbons, they have four different groups. Okay. There are 4 different groups on those carbons. Next question. In the case of this substituted cyclohexane, we will also have to redraw this from the chair conformation to a hexagon. Number this as 1, 2, 3. So the methyl group here is pointing up on carbon 1. So we place that methyl group on a wedge bond. The methyl group on carbon 2 is also pointing up, placed on a wedge bond. The methyl group here is pointing up, so we place that also on a wedge bond. In this structure, we can literally divide this into 2 equal halves. That means this compound has a plane of symmetry. If it has a plane of symmetry, that means it is achiral. This is where I'll stop for today. I wish you the best of luck on your exam.